Hello dear students. In today's lecture, we will try to understand what is Debye shielding and we will derive an expression for the form of the potential which exists within the electron cloud. So far what we have understood is the basic definition of Debye shielding and how we can construct a mathematical picture for understanding the shielding of positive charge or test charge by the electron cloud, right. In the last class, we have derived this second order differential equation, which is d square x by dr square minus x by lambda d square is equal to 0. So, in the last class itself, I told x is not the position coordinate that we are familiar with, rather x is defined to be r phi, where phi is the potential that we are trying to understand, r is the radial coordinate and x is the variable which stands for this. Right. So, lambda d is a substitution that we have made. Lambda d is defined to be square root of epsilon naught kBTE divided by n e square. Epsilon naught refers to the permittivity of free space, Kb the Boltzmann's constant, Te is the electron temperature, n is the charge density or number of particles per unit volume within the plasma, E is the magnitude of the electron charge. Right. Now, we made this substitution to get this equation in a simple terms. Right. Now, we have to solve this differential equation so as to derive what is phi of r. In order to get here, we have assumed the potential to be symmetric in theta and phi, and it has a variation only with respect to r. Right. Now, once we have a differential equation, what we do is we take solutions which are acceptable for this differential equation, and upon substitution of these solutions, the differential equation will be 0 or it will be valid. Okay. So, let us say I take one such solution where x is e to the power of r by lambda d plus b e to the power of minus r by lambda d. This is an exponential solution. X is equals to, because x is the dependent variable here, x is a e to the power of r by lambda d plus b e to the power of minus r by lambda d. Now, if you substitute, you take dx by dr, then you take d square x by dr square and substitute in, we call this equation as 1. If you put this in equation 1, we will see that this solution satisfies the differential equation. Fine. So, once you define x is equals to a e to the power of r by lambda d, b e to the power of minus r by lambda d, we know that x is actually r phi. R phi becomes a e to the power of r by lambda d plus b e to the power of minus r by lambda d. So, phi of r is going to be 1 by r times a e to the power of r by lambda d plus b e to the power of minus r by lambda d. Right. Now, we have to find out the values of these constants a and b. So, generally we know how to do it. The process is very simple. We have two constants, so we need to apply boundary conditions which will tell us what is the value or of this function at the beginning. Then we can get rid of few constants. So, let us say we use the boundary condition number 1 here, which is when r tends to infinity, what happens to phi of r? So, this is not a fact actually, this is something that we impose. Within the given scenario in which we have taken an enclosure in which plasma is present and we have kept it positive charge. The idea is that this positive charge will be surrounded by many thermal electrons whose objective is of course to nullify the charge, but they are not able to do so because of the thermal energy or the inertia that they have. So, as a result, they keep moving around this positive charge and thus constitute a shield of negative charge which will neutralize the positive charge for any part of the plasma which is beyond the cloud. This is the basic objective, right? What it means is that plasma, by the means of its collective behavior, has an ability to shield this positive charge or to make this positive charge invisible for most of it. Some part is of course influenced, but this influence is only to nullify or to make the charge, positive charge, invisible for most of it, right. So, ideally if you want a potential to exist because of this positive charge, so we can write what will be the fundamental nature of potential due to a charge 1 by 4 pi epsilon naught q by r. If you want this potential to exist everywhere, let us say, then there is no point of shielding or there is no idea of shielding at all. But if you want, let us say for example, when r tends to infinity, when r is going to very large distances, we can simply say that our phi of r should be 0. So, at very large distances of r, phi of r should become simply 0, right. Now, let us say you have what the potential phi of r, the solution is 1 by r a e to the power of r by lambda d plus b e to the power of minus r by lambda d. Let us substitute this boundary condition 1 into this equation. Okay. What happens when r tends to infinity, when r becomes very, very large, right? What will happen? This will become infinity, of course, and this will become infinity, but e to the power of minus, right? So, it will be 1 by because of that, right. So, this part will of course become 0 directly, right. Now, if you want the left hand side to be 0, you would expect that this part a into infinity cannot be 0, right. A into infinity cannot be 0, but on the other side, on the left hand side, you have a 0. So, in order to achieve this equality, you must say that a is 0, right. I hope you have understood what I have done here. Phi of r is the potential which is assumed to be existing in this form. This form is perfectly fine with us because it satisfies the differential equation, which is a result of all that discussion that we had. So, this differential equation contains all information about the shielding process, about the potential, about the symmetry of the potential, everything. That means, if you are able to solve this differential equation, then you are actually accounting for the form of the potential which keeps all that shielding intact, as simple as that. Now, when you go about solving it, this is what you get, but what you have is you have two constants a and b. You do not know what those a and b's are. Having a and b's nonetheless still satisfies the differential equation, but we cannot take this constant as it is. We should know them in its full empirical form or analytical form. So, in order to do that, generally the accepted method or the method that we follow is we see what will happen to this solution at the ends of the system. So, when r tends to very large values, you would naturally want the potential to vanish. That is why you take the phi of r to be 0. If you substitute this, so you have this is 0. When r tends to infinity, this is a into e to the power of this exponential of infinity of course becomes infinity, and since exponential of minus infinity becomes 1 by exponential of r by lambda d, 1 by infinity is 0, right. So, in order to achieve this, a into infinity is equals to 0, we require the constant a to be 0, right. What about b? We do not know about b, right. We do not know about b. So, b can be anything, it does not matter, but this term, this entire term is 0 at infinity. So, let us say at that point we can write the potential, the form of the potential as phi of r is 1 by r b e to the power of minus r by lambda d. You understand, this is what I have done. So, if you are wondering why I did not take a, or just now I said it b can be anything. So, b is still unknown for us, okay. But we know for a fact that a has to be 0 when r tends to infinity. When r becomes sufficiently large, the constant a will tend to be 0, right. So, at that point we have b e to the power of minus r by lambda d, right. Let us take another extreme condition or another boundary condition. Let us say when r tends to 0. What happens when r tends to 0? When r tends to 0, you are at the positive charge itself, right. So, in that case, it is natural that we can only expect the potential to be phi of r to be Coulombic in nature, which is 1 by 4 pi epsilon naught r, right. When r tends to 0, you would expect that the potential will be phi is equals to q by 4 pi epsilon naught r. Now, if you use this into this equation, so we have the nature of potential, right. So, phi of r, if you match these two things, what you will realize is e to the power 1 by r is as it is there, b e to the power of minus r by lambda d. This factor has to vanish if you have to. So, then you can probably say that the constant b is q by 4 pi epsilon naught, but for this potential to exist everywhere, you need this constant to be equal to 1. E to the power of minus r by lambda d should be equal to 1, right. Now, going back and using both these things together, we can realize that phi of r is 1 by r a e to the power of r by lambda d plus b e to the power of minus r by lambda d. Using the fact that a is 0 and b is q by 4 pi epsilon naught, phi of r can be written as 1 by r q by 4 pi epsilon e to the power of minus r by lambda d, right. Let us say, so what are the parameters that we have here? One by r times q by 4 pi epsilon naught e to the power of minus r by lambda d. I will write it or rewrite it for convenience like this. Okay. Now, you see what I have done? You have the Coulombic potential, Coulombic part as it is, and then you have the exponential part. This is where things become interesting. Coulombic part and exponential part. Coulombic part has a dependence of 1 by r and the exponential part has a dependence of e to the power of minus r. Lambda d is the length, okay. R is also in the dimensions of length, of course. Now, let us try to understand the meaning of this. If you go back, relook what we have done. We have taken the differential equation, we have assumed a solution for that differential equation, and if this solution has to be valid, we can keep phi of r to be in that form. Then one boundary condition gave us that the constant A has to be 0 at r tends to infinity, and using the other boundary condition we realized that when we are very close to the positive charge, the form of the potential cannot be different than the Coulombic potential. So, in that cases we have 1 by r times b e to the power of minus r by lambda d is there. We still do not know what is b, right. So, if all of this has to be equal to q by 4 pi epsilon naught r, then we said this factor has to be equal to 1 and this b has to be equal to q by 4 pi epsilon. We just have used our prior knowledge and redesignated the constants appropriately, right. So, using all that, we have now got the form of phi of r, the potential in this expression. So, we realize that it is Coulombic in nature for, let us say, yeah, we can say it here. It is Coulombic in nature. So, this part was relevant, or this is because of the constant b, right. So, the Coulombic part is relevant when r is very small, isn't it? Because when r is very small, only then we have this e to the power of minus r by lambda d equal to 1, and all of this become non-zero or not negligible. And this is relevant when r tends to infinity, r is very large. So, what is the meaning of this renewed potential? So, the external test charge effect cannot be felt beyond lambda d, that is what we have to prove. Now, if you see 1 by r and e to the power of minus r, we have two things here. Something decays at the rate of 1 by r and something else decays at the rate of e to the power of minus r. Which is faster? That is the basic question, right. Where is this valid? This is valid at very short distances and this is valid at very large distances. But both of them combinedly exist to determine the nature of potential that is generated because of a positive charge which is kept in plasma. In order to further appreciate the physical meaning of this potential, let us say we take few situations. Number 1, when r tends to 0. When r tends to 0, what will happen? You have q by 4 pi epsilon naught r into e to the power of minus r by lambda t. So, obviously, when r tends to 0, we can expect that e to the power of minus r by lambda d will simply become 1, isn't it? When r tends to 0, you substitute r is equal to 0 in this, you will realize that this exponential is becoming 1. The exponential part becomes 1, which means that this part becomes irrelevant or important. Or in the second situation, we say when r increases, what happens to phi of r? Or when r increases, phi of r will decrease, and the exponential part e to the power of minus r by lambda d also decreases, isn't it? How do I say this? Q by 4 pi epsilon naught r. When r is increasing, the denominator is increasing, the potential, the left hand side will decrease, right. E to the power of minus r by lambda d is 1 by e to the power of r by lambda d. When you have increasing r, you are raising the power of this exponential, the denominator will increase, and as a result the numerator will decrease. With increase in r, the denominator will only increase, and whatever is being accounted for this will eventually decrease. This is what is shown here, right. So, I hope you are able to follow this simple mathematics. Okay. Then we have another situation. Let us say when R is equals to something called as lambda d, because lambda d is there within your picture, right? When R is just equal to lambda d, what happens to phi? Phi of R becomes q by 4 pi epsilon naught lambda d e to the power of minus lambda d by lambda d, right, which is q by 4 pi epsilon naught lambda d into 1 by e. What is it? So, what we can infer is at a distance r is equals to lambda d, the potential phi of r becomes 1 by e-th of the potential. Potential suddenly drops to very small values because 1 by e, 1 by 2.7 something of the original potential. So, at lambda d, the potential is very, very small. Okay. Now, we take another situation where r is equals to 2 lambda d. You have gone beyond lambda d or beyond the device length. Then we can say that as a result, phi of r becomes q by 4 pi epsilon naught times 2 lambda d e to the power of minus 2 or q by 4 pi epsilon naught. I will take lambda d to be separate and e to the power of minus 2 by 2 or phi at 2 lambda d becomes q by 4 pi epsilon naught lambda d into 1 by 2 e to the power of 2. What is the conclusion? The conclusion is that if this is the potential at the edge of the Debye sphere, at a distance of 2 lambda d, the potential becomes even smaller. The potential is getting scaled by nearly 1 by 2 exponential power to the power of 2. So, it is decreasing very, very fast, right. The conclusion is that at r is equals to 0, the potential is phi is q by 4 pi epsilon naught r. We cannot write r is equals to 0 because if r is equals to 0, q 1 by 0, which becomes phi becomes infinity. We will only say that r tends to 0. Okay. Phi is q by 4 pi epsilon naught r. What happened to the exponential term? Exponential term became just 1. So, there is no role of exponential term, right. Let us say, yeah, this is the conclusion actually. Let us try to understand this in the fullest possible manner. 4 by epsilon naught q by r e to the power of minus r by lambda d. You see, this is what we have derived. I am doing it again actually. This is what we have derived. How did we get? This is the constant b, right, and we got this by assuming that when r tends to 0, the potential will be Coulombic in nature. Coulombic potential has 1 by r dependence. And how did we get this? E to the power of minus r by lambda d, we got this basically from the solution of the differential equation itself, nothing else. The solution of differential equation had this term e to the power of minus r by lambda d, right. We know, so now we know how we got these terms, right. Let us try to understand the significance, the physical significance of these different terms. So, this is part from our understanding is Coulombic and this part is exponential. Okay. So, these two represent how the potential will decrease away from the positive charge. What do we want? We want such a picture in which the potential becomes almost 0 once you cross the limit of lambda d, because lambda d defines the length up to which this positive charge's presence can be felt, right. Now, in order to understand this, we have constructed these 4 different cases. In the first case, we took r to the extreme left, saying that r is nearly 0. We know what happens when r is nearly 0. So, because this is self-reinforcing, because we constructed this picture and mathematically we found out those terms which are relevant to prove our assumption. So, this is self-reinforcing each other. So, when r tends to 0, the potential is Coulombic, because the potential is indeed Coulombic, and the other term simply becomes 1. This is what we see here. When both these terms, let us say, coexist, for example, you are moving away from r is equals to 0. This is what the situation is now. At r is equals to 0, at r tends to 0, we only have this term valid, this term becomes simply 1, right. Now, let us move away from r is equals to 0. When r is increasing, what happens? The potential phi of r, which is the Coulombic part, is of course decreasing, and the exponential part is also decreasing, which was just 1, which does not have any variation. Now, it is decreasing as we go away from the r is equals to 0 limit. Both of them are decreasing. When, how fast are they decreasing? You can realize by plotting something like 1 by r and e to the power of minus r. You take r is equals to 0 to 0.1 and use any mathematical tool available online and plot 1 by r and e to the power of minus r. You will realize, although both of these things combinedly decreasing the value of potential, you will realize which is making this decrement very fast. Okay. But the message is very clear: as you go away from r is equals to 0, the potential will decrease. At lambda d, you will realize that the potential has already dropped to 1 by e-th of its value in the vicinity of r is equals to 0, right. So, this is the most important thing. So, at r is equals to 0, there is nothing, we never discuss at r is equals to 0. In the vicinity of r is equals to 0, the potential is something, let us say phi at r tends to 0. The potential at r is equals to lambda d is simply 1 by e-th of this potential. This is the message. So, now the exponential decrease has actually started, which means exponential decrease is a very fast decrease in comparison to 1 by r. Okay. Now, the exponential decrease has started. So, it has reached to 1 by e-th of its original value. You go further ahead, you move away from r is equals to 0 even further, take a distance of 2 lambda d, twice the lambda d, you will see that the Debye's potential, or the potential as a matter of fact, with respect to phi at r tends to 0 becomes very, very small, e to the power of minus 2 times by 2, or this entire potential scales. So, this is phi at r tends to 0. The potential at 2 lambda d becomes 2, this divided by 2 e to the power of 2, right. What am I trying to prove here? I am trying to emphasize that when you are moving away from the positive charge, the potential is up to a particular distance, it is falling with a 1 by r dependence, because it is fast, and after that the potential is falling at a very, very fast rate, which is exponential in nature. Okay. Now, let us say we can reinforce these 4 statements by including one more mathematical step. We can say that if r is equals to 0 and r is equals to lambda d are the limits, we say that, let us say, within short intervals spanning from here to here, r is this somewhere the Coulombic part is very dominant, and after some point the exponential part becomes dominant. So, having said all that, we can now say that the potential inside the Debye's length decreases according to 1 by r, and at the edges when it is about to reach lambda d, it will decrease exponentially. So, we can put it in terms of a simple graph where we take, let us say we take r, the distance away from the center of this positive charge, and this is phi of r. So, the potential would be something like this. which is Coulombic, which is 1 by r, and suddenly at lambda d it will be very fast. So, this is an exponential decay. Okay. All right. So, now we have understood how the Debye potential works and how we can derive an expression for the Debye's potential and the Debye's length. So, there are some more aspects about the Debye shielding that we will try to cover in the next lecture.